So let's define a minimal polynomial. We start with an algebraic alpha over a field f. The minimal polynomial is the monic irreducible polynomial with coefficients in your field that has alpha as a root and divides any other polynomial that has alpha as a root. We proved that this polynomial exists in the last video. The degree of alpha over the field f is the degree of this minimal polynomial. Okay, well, let's see an example of a minimal polynomial. I want to consider alpha, which is this number, over the rationals. So, to find the minimal polynomial, I will begin by letting x be alpha. Then I will manipulate this expression to come up with the minimal polynomial with coefficients that are rational. So I could square both sides. So if I square both sides, I get x squared is 1 plus square root 2. So I'll subtract 1 and find this relationship. Squaring both sides again, I get x squared minus 1 squared should be 2. So my minimal polynomial for alpha over q is I'm going to take p of x to be x to the fourth, so I'm going to expand this, x to the fourth minus 2x squared, and then I'm going to have a plus 1 and subtract 2 on the other side to get minus 1. Now what I've done is, by construction, create a polynomial that has alpha as a root. So alpha is a root of this polynomial, but is it the minimal polynomial? Well, it's certainly monic. And using the techniques that we've developed in previous videos, it's also irreducible over the rationals. At the very least, you could see that it has no roots in the rational because of the rational root theorem. If this did have a rational root, then it would have to be either plus or minus 1, and neither one give a root when you plug it in for x. So there's no roots, and then you can prove that there's no way to factor this degree 4 polynomial into two degree 2 polynomials. I'm going to omit that for now, but it is irreducible. Has alpha as a root, it's monic, and it also divides any polynomial that has alpha as a root. If there was a degree 3 polynomial that was the minimal polynomial, then it would have to divide this degree 4 polynomial, breaking the degree 4 polynomial into a degree 3 and a degree 1, which is not possible because there's no degree 1 polynomial that divides p. It has no roots. So regardless, this is the minimal polynomial, and alpha is degree 4 over q, because this is a degree 4 polynomial. Okay, so let's write down some notation. So let f parentheses alpha, so we haven't seen the parentheses here before. We've seen brackets to denote polynomials, but when I have parentheses, what that's going to mean is this is the smallest field that contains both the elements in your field and alpha. So there are two cases to consider. So when I write this notation down, I'm thinking one of two things. If alpha is algebraic of degree n with minimal polynomial p, then I kind of know what this field is already. from our previous discussions on field extensions. In this case, we have that the smallest field that contains f and alpha is isomorphic to the polynomials modded out by the ideal generated by P. So this is a field because P of x is irreducible by definition. This is a field, and this field, if you want to write down explicitly what the elements look like, this field looks like everything of the form R of x plus your ideal P of x, where R of x has degree less than or equal to n minus 1. So the degree of P is n, so R has to have a degree less than that. Now, if you write this down, this is everything of the form an minus 1 x to the n minus 1 power plus an minus 2 x to the n minus 2 all the way down to the constant term plus my ideal. And these are where my coefficients are in my field. Now, I could say that this is isomorphic to the following. This is isomorphic to an minus 1 alpha to the n minus 1 power. Alpha is this algebraic number of degree n that I have up here, plus an minus 2 alpha to the n minus 2 all the way up to a0, such that a0 up through an minus 1 are elements in my field. So what I've just done here is I've taken, you could think of it as taking the x's and replacing it with alpha. I applied to get from this field to this field, I applied the evaluation homomorphism phi of a. So this is the evaluation homomorphism. I turned this ring into this ring. The evaluation homomorphism in this case is actually isomorphism, because if R1 of alpha equals R2 of alpha, so if I have 2 degree n minus 1 or smaller polynomials that evaluate to be the same thing when I apply alpha, the evaluation homomorphism, then I could subtract and I get R1 minus R2 evaluated at alpha is 0. That would be a contradiction because the degree of R1 minus R2 would be smaller than the degree of the minimal polynomial. What I'm trying to show is that when restricted to these degree n minus 1 or smaller polynomials, the evaluation homomorphism is actually an isomorphism, showing why that these two rings are isomorphic. And this right here, if you think about it for a moment, that is the ring of polynomials in alpha where I have coefficients in my field. So it's all possible polynomials in alpha. So that's what happens when alpha is algebraic of degree n. And the other situation is if alpha is transcendental. So if alpha is transcendental, then here the polynomials in alpha with coefficients in your field is not a field. Why? If it were a field, then the inverse to alpha would exist. So then alpha inverse would be in this ring. So that would mean alpha inverse is some polynomial in alpha. So an alpha to the n plus a0. And this would be a contradiction because then you can kind of multiply both sides by alpha, subtract 1, and thus you can find 0 is an alpha to the n plus 1 plus a0 alpha minus 1, finding a polynomial that has coefficients in your field and alpha as a root. So that's a justification of why this is not a field. So if I want the smallest field that contains f and alpha, I can say that this f adjoined alpha, the smallest field that contains both f and alpha, is isomorphic to the field of fractions for this polynomial ring with coefficients in the field. So what I'm saying is that this, here, I'll do it on the next page. So in this case, your smallest field containing f and the transcendental number alpha looks like everything of the form p of alpha over q of alpha, where p of x and q of x are polynomials in your field f of x, and q of x is not the zero polynomial. Here, let's finish this video with some examples because it's been kind of abstract what I've been saying. So let's do 2 quick examples to finish this video. What is the smallest field that contains the rationals and the transcendental pi? So we've said before that pi is transcendental over the rationals. Therefore, the smallest field that contains these is everything of the form an pi to the n plus a0. So a polynomial in pi divided by another polynomial in pi, bm pi to the m plus b0, where everything here, a0 up through an, b0 through bm, these are all rational. What if I take an algebraic number? So what if I do the field q, and I'm going to add in maybe square root of 2. Well, the square root of 2 is algebraic. It's degree 2. This is the same as the field q with the square root of 2 as an indeterminate, polynomials with in the square root of 2 with rational coefficients. This would be everything of the form a plus b square root of 2, such that a and b are rational. You could even do 2 to the 1/4 power. So the smallest field that contains q and this algebraic number is everything of the form a plus b 2 to the 1/4 power plus c times 2 to the 2/4 power plus d times 2 to the 3/4 power, where a, b, c, and d are rationals. Okay, fantastic. I'll see you for the next video.